Hi there. I'm very happy to talk about my research. My research is primarily on V1 periodicity and V1 self-map, moving from complex-motivic to real-motivic. Also, C2 equivariant is involved. I will give a brief introduction and focus more on recent work. Okay, so let's start with complex-motivic. Here is the E2 page of classical atom spectral sequence. Picture credit to Dan Isaacson. And we can see this vanishing line of slope 1/2. That's the work by Adams. And later on, Peter May established this V1 periodicity line of slope 1/5. So what does this line tell us? Above this line, we see those repeated patterns. So those are given by applying the V1 periodicity operators. And this line is saying above this line, apply that operator is giving you an isomorphism. So moving to motivic, complex motivic, things are different. And one of the difference is the class eta detected by H1, that is nilpotent classically, but not anymore in complex motivic. So those H1 towers are elevating the vanishing line to be slope 1 because they are slope 1. That's the work by Guillou and Isaacson. And I am filling in the gap and establish this V1 periodicity line in complex motivic. So I did lost control on those H1 towers, but that's okay because we already know all the positions of those H1 towers. So great, and then I switch gear to our motivic. That's joint work with Prasit, Bhattacharya, and Weiser, Bertrand, Guillou. Our motivation arises from chromatic homotopy theory. So we know there's periodicity theorem connecting the notion of type N spectrum with Vn self-map. In particular, if we look at this Y, built by smashing together the cofiber of 2 and cofiber of eta, that is of type 1. And so it emits a V1 self-map. And why do we care about a self-map? Well, we know this cofiber is realizing A of 1, which is the Steenrod subalgebra. So we would like to see this picture in our motivic as well by saying that I had better talk about the connection between our motivic and classical. So let's talk about things in the middle, that is the C2 equivariant stable homotopy category. We get two functors. One is the restriction functor for getting down the action, and we have this geometry fixed point functor. So they are all from the C2 equivariant stable homotopy category back to classical. We also have this steady realization functor connecting our motivic and C2 equivariant. So in summary, we have two paths from the R motivic back to classical, stopped by C2 equivariant in the middle. And that allows us to get a type N, K spectra in the R motivic setting defined while pulling back along those paths. So this idea is inspired by Balmer and Sanders' work. They stop at the C2 equivariant and we go one step further. Strickland also contribute to this idea. Okay, so we define the R motivic spectrum to be type N, K if the underlying is of type N and the geometry fixed point is of type K. We also define V N, K self-map analogously. Under this notion, we can cook up our spectrum Y in our motivic. So that will be the cofiber of H and the cofiber of eta smashing together. Here, H and eta, they are both the R motivic version of half map. And our theorem is about that the Y we find admits a V1 common U self-map, whose cofiber is realizing the R motivic Steenrod subalgebra A1. So great, we find one realization of A1 in our motivic. Well, we would like to discover more about that story And the first step is we want to understand how to extend A1 as a full A module in R-motivic. So actually, there are 128 different ways to extend that. And by a version of total realization theorem, also is weak form, we figure out all of them can be realized. So that's exciting, but let's relax a little bit and look at what AF1 looks like in R-motivic. So we can see there are enough spaces for more interesting things to happen. For instance, this bottom class potentially supporting a square 8. This is not happening in classical because you don't have enough space for that. Okay, cool. So we also have this configuration theorem that is arising from the fact that both the underlying and the geometry fixed point induces maps between the C2 equivariant cohomology and the classical cohomology. So roughly speaking, yeah, they also interact with the Steenrod operations. The underlying of the equivariant square n is giving you the non-equivariant square n back. And this phi hat is called the modified geometric fixed point in the sense of Hill and Hopkins. Why? Because we know that the geometry fixed point of the Eilenberg-MacLane spectrum is polynomial. That is not giving you a class in cohomology, so you need to do one step further, projecting it down to the zero vector. So this is this applied to equivariant square 2n is cutting it in half and giving you non-equivariant square n. We use this information to classify those 128 extensions. So before I reveal those relations to you, let's recall what A1 looks like. So here, each dot is a copy of coefficients M2, and this dotted line is indicating it's getting the tau multiple. The right side is its geometry fixed point. So notice that none of the square 4 or square 8 is drawing in, so not the A module structure is not defined yet. Okay, so the relations are here, and those Greek letters, they are placeholders. They can be 0 or 1. And the one I highlighted, they are independent from each other. You can count there are 7 of them, so that's how we get 128, that number. So passing this relation down through the modified geometry fixed point, you get another group of relations on the geometry fixed point of A of 1. Okay, cool. So here are some beautiful things. If you collect those placeholders that are independent from each other and list different cases like the codings here, they actually corresponding to the beautiful picture next to that. So here you have different places for square 4 to happen, and then passing through to the geometry fixed point and using a trick of change of faces, you can get this diamond shape or this joker shape. So that is very beautiful. And there are more of that. All right, so to wrap up, it is ongoing work that we are finding more realizations of the full A module structure of A of 1. We do have one, and we know they can all be realized, and we would like to find more. Also, classically, there's the spectrum Z, which emits a V2 self-map whose cofiber is realizing A of 2. That's the work by Bhattacharya. We would like to see if that's also true in R-motivic as well. So thanks for watching, and please stop by my breakout room or email me if you have questions. Thank you.